Hello, I am Arnad Mukherjee and today I'll discuss how to write an assembly code for 8085 microprocessor to find all factors of an 8-bit number. So first, the steps for writing assembly level code. First, we properly write down what our objective is to understand it properly. Now, this objective may be very complex, so we divide it into various subtasks that we can solve separately. Then we create a flowchart algorithm for these separate subtasks. That is, we solve these different subtasks. Then we combine the different flowcharts into a final flowchart that we understand properly. And now that we have understood the algorithm to solve this problem efficiently, we write the assembly code from this flowchart. So now we have to understand what our task is and what our subtasks are. So to find all factors of a number, we iterate from 1 to the number itself and check whether each number is a factor of the original number. This is the overall algorithm that we'll follow. But there are several subtasks here. We need to first understand how to understand whether a number is a factor of another number. To check if each number is a factor of the original number, we divide the original number by this new number and check if the remainder is 0. But again, we need to know how to find if a number is how to find the remainder when two numbers are divided. To find the remainder, we use the concept of division as repeated subtraction. We subtract the smaller number from the bigger number repeatedly until we can't. That is, the number that was originally bigger is now smaller than the smaller number. The number that we obtain now is the remainder. Then we can check if the remainder is 0, and if it is 0, it is a factor. Then we continue on. So first we have the flowchart, the overall flowchart to find all factors. As you can see, we start, then we read n, we input a number n, then we set I as 1. This is the variable that will iterate from 1 to n, and which is the variable that we'll use to check if it is a factor. Now if I is greater than n, then we have already checked all numbers from 1 to n and we can end the program right now. But if I is not greater than n, that is I is less than or equal to n, then we continue. We check if I is a factor, that is n divided by I gives the remainder 0, and we output as such. If the remainder is 0, then we print I. We output that I is a factor. Otherwise we don't. Once this is done, we increment I by 1 and then we check if I is greater than n again, and we continue. Now, in assembly code, there is no specific direct way to check if the remainder is 0. So we need to create an algorithm to check if the remainder is 0. So this is the flowchart to check if a number is a factor of another number. So here we enter two numbers which are to be divided. If A is less than B, then A will be the remainder when A is divided by B. So now we check if it is 0. If it is 0, then it is a fact. Then B is a factor of A and we output as such. Otherwise, it is not a factor. If A is greater than or equal to B, we subtract B from A and then we check again. Now we have the two flowcharts. We combine them to get a final flowchart. This is the final flowchart. And here I have used the correct variables as the same that I'll use in the code. So first we read a number B. Then we set a new variable C equals to 1. Then again, this is the variable that will iterate from 1 to B. We set a variable A as B. Now at this point A is equal to B. So checking if A is greater than or equal to C means checking if B is greater than or equal to C. If it is not, then that means C is greater than B, and we have checked all numbers from 1 to B, so we can end the program right now. If A, on the other hand, if A is greater than or equal to C, then we can continue with the program. Now we check if A is less than C or not. If it is, then A is the remainder when A is divided by C. So we check if the remainder is 0. If it is, then we will print the number. Now here I have changed the value of A to C for reasons that we will see later while we are discussing the code itself. We print A, and then while on the other hand, if the remainder is not 0, then we don't. Once this is done, we increment the value of C by 1 and we send it back to the original place where A is now again loaded with the value of B. Now back to the original decision. If A is not less than C, then it is not the remainder when A is divided by C. So we subtract C from A and we continue the program again and again. Now we will look at the code. This is the code. We will not discuss it here. We will now go to the simulator where we will discuss the code, and then we'll run a few examples. We are here at the simulator with the code, and we will discuss the code and then run a few examples. So the first line of the code, lxid comma 0000h, we're initializing the output pointer. We're initializing the value from which the memory in which the factors will be written is initialized. Then in00h, this will take input of the number from the IO port 00. As we know, when we input a number in 8085, it is loaded into the accumulator. So MOV B, A loads the number into register B. MVIC, 1, we initialize register C with the value 1. Now MOVA, B, we load the number into the accumulator. Here the operations will take place. You will also note that I have placed pointer C1 here so that we can jump back to this position from a different place. Now CMPC, we compare the values in A and C. Now if A is greater than or equal to C, then the carry value will be 0. So J and C will be 1. Now when J and C is 1, we go to C2 position. If it is not, then A is less than C, and we have already checked all the numbers from 1 to B, so we can end the program right now in line 8. However, if it is in fact greater than or equal to C, then we'll go to line 9, C2, where we compare A with C. Now if A is less than C, then JC will be 1, and we will go to block 1. Now in block 1, this means if A is less than C, then A is the remainder when A is divided by C. So in block B1, we use CPI 0H. This will compare A with 0. If A is 0, then JZ will be 1. When JZ is 1, then we will print C. We'll go to the print area in C3. Here we load C into the accumulator. We do this because we can only transfer data from accumulator to memory. So STAXD will load data from the accumulator into the output array. Then INXD will increase the output pointer by 1, and we'll go to C4. Now in line 14, C4 increases C by 1, and then C1 sends it back to the place where the value of B is loaded onto the accumulator. Now going back to line C2, if A is in fact greater than or equal to C, then we know that A is not the remainder, so we should decrease A by C, as we will in line 11, JNCB2. We go to block B2, where sub C decreases the value in the accumulator A by C. Then going back to C2, where we compare A with C again. So this is how our code works. Now we will run a few examples. So first we will use the value 3. We know that the factors of 3 are 1 and 3. So first we'll assemble our program. A program assembled successfully, and we'll execute it. Now we go to the memory and see that in the memory we can see our data 1 and 3. Now we'll understand how this happened. In line 1, the output pointer is initialized, then 3 is inputted, and in register B the value 3 is stored, and in register C the value 1 is stored. The accumulator A now has value C. A is now compared with 1. Now A is greater than or equal to C, since 3 is greater than 1, so we'll go to line 9 in C2. We compare A with C. Now A is not less than C, so we'll go to line 11, JNC B2. B2 in line 16 decreases 3 by 1. 3 is now 2. Now we go back to C2. Again we compare 2 with 1. 2 is greater than 1. So again we decrease 2 by 1. It is now 1. Again going back to C2, we do this until the value in the accumulator is 0. Then according to line 10, since A is less than C, we send a check to see if the value accumulator is 0 in block B1. In B1, we use CPI0H. Since A is 0, we will go to the printing area 3. We load the value 1 into the accumulator and then we move it into the data. As we can see in address 0000, the data is 1. Then we go to line B2, where C4, where C is increased by 1, it is now 2, and we go back to the original area. Now again the value in the accumulator is 2. 2 is compared with 3, 2 is greater than or equal to 3, so 3 is greater than or equal to 2, so we continue. Again comparing the values in A and C, A is not less than C, so we decrease A by C. Going to B2, 3, the value in accumulator is now 1. We go to C2 again. Now 1 is less than 2, so we send a check for 0. In B1, 1 is not 0, so we don't print it, and we increase the value in C by 1. C is now 3, we'll go back to C1, and the accumulator will be loaded with the value 3. We'll compare it with 3. Since 3 is still greater than or equal to 3, we'll continue. We'll compare 3 with 3. 3 is not less than C, so we'll decrease 3 by 3. It will be 0. Again, when we're comparing 0 with 3, 0 is less than 3, so we'll send a check for 0. It is 0, so we will print it, and in address 0001 we have the data 3. Now again it will be incremented by 1. The value in C is now 4. We will compare the value. A is now 3 again. We'll compare the values in A and C. Now A is less than C, so the program will end here. Now we'll try with a bigger number, one that has more factors. 4. Data, we have 4, and we execute the program. Now in memory, we can see the data 1, 2 and 4 as the factors of 4 should be. And finally we try with a very big number, 48. We execute the program, and in memory we have all the factors of 48, 1, 2, 3, 4, 6, 8, 12, 16, 24 and 48. Thus we have written an assembly level program to find all factors of an 8-bit number. Thank you.